reminder, next Thursday we'll have class here from 12 to 2:30. I don't want to give you too much hard time. And bring your class notes. And also, I would like to ask somebody to bring the book in. I'll bring my copy. And can somebody bring the book in? Nobody has taken the book from the library? I bring it. Hey, are you lame or what? You have hands, right? So raise your hand and say, yes, I will. Okay. Would you be so kind as to bring it on Thursday?
Yo lo he cogido una vez y si no hay reservas, sí te lo dejan coger otra vez.
I will. You will. Okay, thanks. I don't know if I told you, I'm following the book. Yeah, okay. Just to be sure. And so I will make. Okay, so I'm going to write this for you. Okay,
how many times?
How many?
How many times?
How much time? Okay, how many times means cuántas veces? How much time? Yeah, it will be around 2 hours and 30 minutes. Okay, more. Yeah. I mean, are you interested in passing this course? Okay. Okay, so review problem set 1. Review problems 1 to 10 from problem set 2. And I'll bring extra material, which will be very close to what you get in the exam. Right? So we are going to practice some definitions, tests, questions. Things like that. It's good to learn, but it's good to pass. Right? Okay. Yeah, that whispering of learning. So, I don't know if I should start by reviewing everything, or you don't need it. Are you up to date? No, what? Okay. So, brief review of everything. I may be insulting because you might have this in your mind already. So, this is combinatorics, right? Which is counting. And counting basically consists of, yeah, the third word, consists of, people keep saying consist in, incorrect, that's why I write it down. Counting consists of taking a problem and apply some transformation so that it becomes a known counting problem. Can you tell me an example? Remember the problem of counting the divisor of 19,000? It was transformed into counting things about these two sets. Right? Then, in order to, what's those known counting techniques? Well, here you have basis 1, the sum rule, which tells you that the cardinality of two disjoint sets is the sum of the cardinalities. Yeah. Then, product rule. Which tells you how much is the cardinality of the Cartesian product. Then we have what? Who said that? Congratulations, man.
So you have studied? Okay, I'm touched.
Don't do that to me too often because you have heart problems. So here we have inclusion-exclusion principle. Very good. Which tells you, I'm going to write it. I'll just leave it like that. So there's a formula there, and then there's a big branch coming out from here. Counting lists or strings. That was the same more or less. Okay, so an n-element string formed by taking out elements from a set A with n elements. This is called what? Another heart attack. It's called what? You look like you know the answer, no? Permutations. But you may be interested in just taking R whole thing. And then you have r-Permutations. Okay. So far so good. And then here the order was crucial. But when we remove the order, when the order doesn't matter, what we have is just elements. And then we have combinations. Right? With the binomial coefficients, whose definition is as follows. Right? And from here, we went to binomial theorem, which was invented by Newton, although in English it's not called Newton's theorem, it's called binomial theorem. It says, it states that x plus y to the nth is in this expression here. And at that point, I introduced a very important concept, which was combinatorial proof. And thanks to that, I don't like to use this part of the blackboard, but it's better that way. So I proved this thing. This is called Pascal's identity, and also prove several things like and also I gave a couple of boring algebraic proofs. I made a point that the combinatorial proofs are good because they imply a wider definition of the matter. An algebraic proof is just some computation that you do perform to prove a specific case. Combinatorial proofs are wider in scope. You don't know this. Scope, alcance. Okay, so you clever guys, what's missing here? I'm going to explain something new, which is what? Because up to this point, everything was without repetition. Right? So here it was without repetition. And now I'm going to introduce repetition. We did a little bit of repetition here with the product rule, but now I'm going to go further down. And also I'm going to introduce repetitions here Who has done this chart already? You haven't done this for yourself? No? Can I qualify you as a university student if you haven't done this? Okay. What's first? Okay, important notation of what's followed is not in the book as such, so pay attention. This is one of the few occasions where I depart from the book. Okay, so repetitions. Now I want to form, this will be the easiest one. I want to form an n element string by taking elements from A. This is R. And I have n elements. Obviously, as I said, elements can be repeated. So, answer, solution, it should be very easy. It's just a straightforward application of the product rule. Yes, n possibilities here. N possibilities here, but because there are repetitions, so forth, so on. That's one version, successivamente. And this gives you n to the off. This number will be notated as permutation on repetitions and R. Okay. Little example. How many letters does the English alphabet have? 26, right? I say that because if you do the problems on the book, you must know that. It is mentioning that fact all the time. So, how many three-letter strings can be formed? Yeah, 26 to the third. Right? Okay, this was very easy. Okay, something more difficult. Sorry, here I forgot to say r-Permutations because I'm taking just upset. And now this is permutations. with the repetition. Okay. Suppose I have this set. How many permutations of that set can I count? Okay. Yeah, I'm a loud guy, so I want him to study in a quieter place. So, how many? 5 factorial. Okay, and now I'm going to play another game. I'm going to substitute these elements by this. Now, how many? The answer is not 5 factorial. As a matter of fact, well, this is a lovely expression you should learn. And wow. As a matter of fact, de hecho, por supuesto. So how many and how and why and who? How? Why do you say that? Because you are subtracting what? 2 factorial. Why? Well, factorial is 2, right? And easily I can make more than 2 right away.
3 factorial plus 2 factorial? No.
That's the classic mistake, but it's good that you make it here now. No. Suppose that write this. For example, and I turn this into A, I turn this into B, and I turn this into A. I get one of those, right? One of my permutation, what I'm looking for, right? So that gives you an idea of this argument has already come out. It's not the first time I use this argument. Okay, one more attempt. Suppose that I write little subscripts here. When I write sub 1 means A. And then I write 2. I count all permutations and I see that there are 120. And then when I have 1, 1, 1, I just write A. Right? So, if I have A, B, B, this may be A1, B1. Let's change this. Something like that, right? How do I transform this into this? For the A's, for example.
5 factorial minus 3 factorial?
No. And minus 2 factorial. That's the same idea as yours, but it doesn't work. So, one of those, I mean, the idea is once I fix the whole permutation, if I permute the A's among them, my choice doesn't change, right? So, all that permutation must go to just 1. And I told you in a previous class that when you do that, you divide. So here you have 5 divided by 3. This corresponds to A.
Plus 2 factorial.
No. 1 times 2 factorial, which corresponds to this, right? So remember that day that I wrote all the permutations and say this corresponds to 1, and we made all the computations. So okay, in this case, annotation here is very important. You have permutations with repetition, semicolon, so this is different from here, right? It's just a semicolon. Please be very careful about that. I'm going to place a semicolon here. For example, there is a funny example here. You know this word? It's the name of a river in the United States. How many permutations, different permutations of that word can I form? Well, there are repeated elements. So I have, in general, it would be 2, 4, 6, 8, 10. I have 10 letters, and then I see several repeated elements. I have, I don't know, maybe the I. I have 1, 2, 3, 4. This is for the I. Comma, then the S.
So this is 3.
3, that's for the S, and then I have 2 E's. Right? Whatever number comes out. Right? Okay, and now we go to the core. Okay. This is the hardest counting problem you are gonna face, for sure. So it is quite abstract. So I'm going to start by trying to solve a practical problem, a given problem, and then I'll deduce the principles behind that. So here I have an equation. Where n is a positive natural number, so r is okay. The question is, Ideas. You like thinking, right? No? Why are you here? Just go and become a cash dispenser at the Carrefour. I mean, thinking gives you pleasure. Not that pleasure, but another kind of pleasure. If you get me. So, ideas how to solve this? Future computer scientists. Future, well, I mean, maybe 10 years, but future. Certainly. How can I solve that? Well, there's another condition. To make it easier at the beginning, let's say that everything is possible. Right? I want integer natural solutions of that equation. Ideas show me your creativity. I told you that mathematics was about creativity and not about screwing you up. You have such a lack of vocabulary, I can say whatever I like. You don't care, you understand. I just said that this is about creativity. It is not about sending you to it's not about failing you. So just show me you have just €1. I mean, I know that the rest is devoted to sex and things like that, but just €1. Could you focus that euro on this? Why? And a white man.
Because there are components in it.
Yeah, well, that's a start. I mean, I didn't say give me the right answer right away, just an idea, whatever. You said N to the R? Those are too many. Those are too many, because this corresponds to a string formed by numbers here. But I'm talking about sums, right? About summation. So, yeah, well, this is the first approximation, but we see it doesn't work. I mean, we cannot apply previous approaches, previous methods. This is not about permutations or permutations. So, well, I'll reward my question. How would you, how would you build the solution? Forget about counting. How would you build the solution? How would you get the solution? First of all, I know that all the variables must sum n, right? So I'm going to think, say that I have a set A with n objects. What would the next step be? So you're given a bag with several elements there. How do I simulate the solution using my bag full of balls, for example? Suppose I have a bag with n balls, and I want to simulate the solution of this equation. Yeah, more.
elements.
How many? Just one subset?
Well, you will have a lot of subsets.
How many? R subsets, yeah. Have to form R subsets. Right, that's nice. Which corresponds to saying something like that. Right? Where here we have R subsets. Okay, that's an idea. That's an idea. Then what I'm going to do is the following. Well, first of all, I have a question here, and that's why there is the word repetitions here. When I suppose this subset has 2 elements, do they matter? No, not really. That's why you see repetition. Okay, so the idea to solve it, which is a very clever one, is the following. Here I have n. I don't care about the elements. I care about the number of elements in each subset. So I'm going to write n stars, which represents this set here. And now I'm going to write down r minus 1 bars. Does anyone know what n minus 1? And what are those bar for? Okay. I carry on. Then I'm going to compute all permutations of the whole set here. Well, I have to be a little bit careful, right? Are you okay, Bob? You have a very big mouth. I could even see you in your throat. Unbelievable. So, we have to be a little bit careful because here we have repetitions. Right? So suppose one of those permutations would be something like that, right? And I said I have to be careful because I have repeated the stars, I have repeated the bars. The bars are like dividers. So once I have this list here, then I have a solution of this. Why? Because up to the first bar is going to be x1. Up to the second bar is going to be x2. And so forth, so on, and this is going to be xr. Why do I have, sorry, it says n minus 1, this is r minus 1. Why do I have to use r minus 1? Because with one divider, you have 2 sets, right? 2 subsets. That's why if you want to have r boxes, you need r minus 1 dividers. How many of those permutations of what?
And plus r minus 1.
Yes, perfect. Where r and repeated and repeated. Okay, so I'm going to write down the numbers for this. repetitions and R. This is not on the book either, so take note of it. Oh, by the way, this will go in the exam for sure. I'll make sure that that's a very important learning goal. Apart, jokes apart. And two things left for today. Okay. So I said I'm going to give you the example, and now I'm going to define what a combinations with repetition is. Just one more thing. This number, because sometimes people define it otherwise, this number is also that number, right? Because of the properties of the binomial coefficient. Sometimes you see this number defined as this or as this. I'll be using this, but I accept that one too. Just a notation matter. And finally, combinations with repetition. What's combinations with repetition? So you have boxes. You have n objects in total, and what matters is not the order, it's how you distribute the objects. So here, you clearly see that if I have, I don't know, K1 here, K2, blah blah blah, Kr, the order among these elements doesn't matter. Right? Remember here, if I permute these two guys, I'm getting the same solution, right? Am I not? So the order doesn't matter. So the order in each box does not matter. In fact, if I permute the boxes, well, I get the same thing, right? Here, I have my equation. If I write it backwards, it's the same thing, right? What counts is that I have a box called R, I have a box called 1, right? So, what matters is the distribution of the n objects in the boxes. So identify this in a normal problem, you know, with natural language, is kind of hard. So on Thursday we'll be doing lots of them. For example, typically, you are a waiter and you have like four customers, and you have to take dessert. So you have apple, banana, oranges, and strawberries. So you have many repeated elements for each, and you have to distribute in 4 boxes to your customers. as a typical example of a combination with repetition. Okay, our guidelines, our flyers, questions, suggestions, comments, phrases. What's phrases? Elogios.